Hi, in this chapter we are going to learn on how to perform a few hypothesis testing. And the first section 8.2 is about the basics of hypothesis testing. Let's consider the following scenario. Our class had 50 students. 25 students are junior and the other 25 students are senior level. Now that I have 20 movie tickets from a friend and that I want to give out these 20 tickets to 20 random students in the class, it turns out that 19 senior students receive the tickets and 1 junior student receive the remaining tickets. Then the student in the class make a claim that I do favor the senior students. It is true. Okay. Or using the statistical language, they are saying that the probability of senior students getting the tickets is larger than 50% or P is bigger than 0.5. If this is a random process, then all the students they should have an equal chance of getting the ticket, which is 50%. So in this chapter, we will present the standard methods for testing certain claims that you see here. Or in this specific case, the senior students are more likely to get the tickets, or P is greater than 0.5. Okay, before we are doing some testing, let's learn about the definitions of a basic words here. Hypothesis is just a claim about a population parameter. This could be a proportion, a mean, standard deviation, or variance. Example: the average GPA of high school students is larger than 3.0. So they claim that the GPA for the high school students should be higher than 3.0 or the mu should be bigger than 3.0. Okay, this is the claim, and we are learning on how to reject or do not reject the claim in this chapter. The next word is the hypothesis test or the test of significance. This is just a procedure for testing the claim that you see here about a population parameter, and we usually use the samples data. We collect some sample data and then we do some testing, because there's no way that you can gain access to the entire populations. We cannot get all the information from the entire populations here. That's why we only use the sample data. There are two types of statistical hypothesis. The first one is called a null hypothesis, or H0, and then the second one is the alternative hypothesis. H0 is just the statement that the value of a population parameter such as proportion, mean, or the standard deviation is equal to some claimed value. And this statement has no change, no effect, or no difference, and is assumed to be true until there is an evidence to prove that this is not true. Now, the alternative hypothesis is the statement that the parameter has a value that is somehow different from the null hypothesis. And this is the statement that we are trying to find the evidence to support, or the statement that has some changing that has occurred different from the original circumstances. So if you go back to the earlier example we saw here, now in the original circumstance, then we should expect that the P should be equal to 0.5. This is the chance for each student to get the tickets, and it should be 50-50 for senior or junior. That's why this is the null hypothesis without any changing, no effect, no change, no difference. That's why it should equal to P equals 0.5. And remember that the null hypothesis always involves the equal sign. And then the alternative hypothesis is that it is different from the original circumstances, or in this case, the P is claimed to be bigger than 0.5, or this should be the alternative hypothesis. Okay, now there are three types of hypothesis testings: the two tails, the left tail, or the right tail. Now we conduct the hypothesis test by assuming that the proportion, the mean or the standard deviation is equal to some specified value. And therefore, the null hypothesis always involve the equality. Right? We have these parameters, they are equal to some specified value, and therefore it should equal to something, or the null hypothesis should involve the equal sign. For the two-tailed test, the null hypothesis, the parameters should be equal to some value. That means we only focus on the two tails, the left tail and the right tail. And then the alternative hypothesis should be different from some value that we have for the null hypothesis. And this is the two-tailed test. So the different side here represent for the two-tailed test. Now for the left-tailed test, the null hypothesis, the parameter is equal to some value. Yes, the same thing as before. And now the alternative hypothesis is saying that the parameter is less than some value. So less than psi, we are using the left portion of the tail or the left tail testing here. And you can think of this way. This is the less than psi, or the arrow is pointing to the left. So we are doing the left tail test. And then the right tail test, the same thing. The null hypothesis is always the parameter equal to some value. And then the alternative hypothesis is that the parameter is bigger than some value, which is the right tail. Or you can think of this way. The arrow is pointing to the right, so it should be the right tail test. Okay, now we never support or we accept the null hypothesis H0 or H0 because we cannot gain the access to the entire population, and we cannot know the true population parameter of 100%. Therefore, we never support or accept the null hypothesis 100%. We never support or we never accept that because you just simply cannot get all of the information from the entire populations. Now we instead use the language that, or the phrase, fail to reject the null hypothesis. If we can find some evidence to prove that, okay, we cannot reject it. That means we fail to reject, but we don't say that we accept it. So fail to reject and accept, they are different. And this means that we don't have enough strong evidence to warrant the rejection of the null hypothesis. But in the same time, we don't have enough or all the evidence to claim that is true. Okay, and this is like the court system. We never say a defendant innocent, but instead we are saying that they are not guilty. They are not guilty means we don't have enough evidence to prove that they commit the crime. But at the same time, we cannot be sure that they are innocent because we just don't know completely everything. Okay, so the same thing to this scenario. For example, suppose we want to determine whether a coin is fair and balanced. A null hypothesis might be that half the flips would result in the heads, and then the other half of the other flips would result in the tails. And then the alternative might be that the number of the heads and the tails would be very different. And we can express this hypothesis using the symbol that we talk about here as follows. So the null hypothesis should be something that involves the equal sign. So in this case, we are saying that if the coin is fair, then the proportion should be 50% each, or P should be equal to 0.5. This should be the half of the flip would be the head and the other half would be the tail. So this is the null hypothesis is the equal to 0.5. And then the alternative hypothesis should be that something is different from the null hypothesis, and we don't say that there's more heads or there's more tails, so it should not be the left or the right tail, but we just say that the number of the heads and the tail would be very different, and the different means that we use the symbol of the different, the equal sign with a dash. Okay. Another example, a pharmaceutical company is producing the Advil pills for 250 milligram dose. However, the manufacturer is worried that the machine that's making the pills had come out of the error, and they should make less the dose than it should be. Okay, so how do I write this one using the null hypothesis and the alternative hypothesis? The null hypothesis again is always involve the equal sign. In this case, we are talking about the milligram or something about the mean of something. So it should be the mu. This is the mean. So the claim is saying that it should be something less than. It should has less dose than it should be. So without no changing nothing, no changing, no effect. Go back to here. So no change, no effect, or no different, then it should be equal to 250, and it does involve the equal sign, or it should be the null hypothesis of H naught. And then the alternative hypothesis, that means it's making less than the dose that it should be, or the mu should be less than 250. And because we are not having the equal sign, so it should be the alternative hypothesis. So the original claim, which is the null hypothesis, is saying that if you buy an Advil, one bottle of 250 milligram, then you should expect that every pill has the amount of 250 exactly. However, we are trying to support the claim that, which is the alternative hypothesis, that the mean doses for the pill is less than 250. Okay, so let's go on to the next one. Errors in hypothesis test. At the end of the hypothesis testing procedures, we either rejecting or failing to reject the null hypothesis. So after doing some testing, either we reject the null hypothesis or we fail to reject the null hypothesis. Remember, we never accept or support the null hypothesis. And because we are doing some testing procedures, it's always having some error. There's nothing for sure 100%. So sometimes we do have errors. And that's two types of errors here. We call that to be type 1 error or alpha, or type 2 error or beta. The type 1 error, alpha, is the case when we reject the null hypothesis when it is true. And the second type of error is the beta, or we fail to reject when it is false. Okay, so go back to this table here. Now this is H, the null hypothesis is true. This is the alternative hypothesis is true. The conclusion that we do not reject when it is true, when the alternative is true, we fail to reject when the alternative hypothesis is true. That means we are in the type 2 error. Type 2 error. That means we fail to reject when it is false. Okay? We fail to reject when the null hypothesis is false. And then the type 1 error is right here. That means when we reject the null hypothesis when it is true, when this is true, and we reject it, we have type 1 error. Okay? Alright, so this is just a quick summary of the table that shows you that type 1 error is when we reject the null hypothesis when it is actually true. And type 2 error is when we fail to reject when the null hypothesis is false. Okay. The null hypothesis is false, meaning that H1 is true. So type 2 error is right here. Do not reject when H1 is true. That means when H0 is false. Now, please note that the alpha, which is the level of significance, this is the same concept that we saw in chapter 7 for constructing the confidence intervals. It is just the probability that the type 1 error, or the probability of rejecting the null hypothesis when it is true. it is chosen by researcher before the sample data is collected. And usually this value is given to you in the problem. Okay, let's try one example here. According to the Centers for Disease Control, 15.2% of American adults experience migraine headaches. Stress is a major contributor to the frequency and intensity of the headaches. Now, a massage therapist feels that she has a technique that can reduce the frequency and the intensity of the migraines, determine the null hypothesis and the alternative hypothesis that would be used to do the testing for the effectiveness of the massage therapist techniques in this case. So, the null hypothesis is always something that involves the equal size. In this case, without the massage therapist doing any changing, doing anything to the body, then we had 15.5%. This is the percentage, or this is the proportion, or we are using the P. So 15.2% of American adults, they have the migraine. So P should be equal to 0.152. If we convert it to the decimal, so moving 2 places to the left. So without before any changing, we had this number. And now after they are doing some techniques to help to reduce the migraines, then the alternative hypothesis is saying that the proportion should be less than that, because after you apply some massage, then we should have less the number of the people, or less percentage for the people that experience the migraines in this case, or P is less than 0.152, or the error here is pointing to the left, which we will have to use the left tail test. Now suppose that a sample of 500 American adults who participate in the massage therapist program, and the result is saying that in the data they indicate that the null hypothesis should be rejected. Provide a statement that supports the program that we have here. So we should reject the null hypothesis, meaning that we do not support the first line here. So there is sufficient evidence to conclude that the therapist techniques reduces the frequency and the intensity of the migraine headaches in American adults below 15.2%. If we do reject the null hypothesis, that means we have enough evidence to say that the program is effective. It's helped to reduce the number of the percentage of people having the migraine down to below 15.2%. And then suppose that in fact the percentage of a patient in the program who experience migraine headaches is 15.3. What is a type 1 or type 2 errors? Now, this should be the type 1. Why? Because in fact 15.3% still have the headache, or it is not less than 15.2. It should be bigger than 15.2, or we should not reject the null hypothesis. Now, because we reject the null hypothesis when it is in fact true, so it should be type 1 error. We reject the null hypothesis when it is true, which is type 1 error. Okay, so how do I testing a claim? There are 3 methods that we can perform a testing or making a conclusion whether we should reject the null hypothesis H not, or we fail to reject the null hypothesis. And then the 3 methods that we learn in this chapter, they should be using the p-value methods, critical value methods, or using the confidence interval methods. Now the p-value methods and the critical value methods are similar in the sense that they always give you the same results, while the confidence interval, the one that we saw in chapter 7, is sometimes different from the p-value or the critical values. Therefore, it is recommended that we use the confidence interval to estimate a population parameter only, not for the testing. Now, in addition, because many technologies, including the TI-83 or 84, they can give you the p-values, and therefore we will focus mainly on how to use the p-values methods in this chapter. Okay, so how do I identify the statistic that is required to test and determine the sampling distribution in the testing? So usually we have 3 parameters. We are testing about something about the proportion p, the mean, or the standard deviation or the variance. Now, we use the same distribution that we saw from chapter 7. For the proportion p, we are using the normal z for the sampling distributions, and the requirement is that np0 it has to be bigger than 5, or nq0 it has to be bigger than or equal to 5. And this is the test statistic that we saw from chapter 7. And then for the mean, there are 2 cases. If the population standard deviation is not known, then we are using the student t distribution. If the population standard deviation is known, then we are using the normal z's. So there are 2 cases. This is the student t, this is the normal z. And then make sure that the sample size is bigger than 30. If not, then we have to make sure that the population should have a normal distribution. And in the last case, when we are testing a claim for the standard deviation or the variance, and we have to use the chi-squares. Now this has a stricter requirements. Make sure that the population has to have the normally distributed data, or we can use the normal probability plot to verify this one. Okay, so using the p-value or the critical values. Now the p-value is just the probability values. P stands for the probability values. This is the likelihood or the probability that the sample will result in a statistic such as the one obtained if the null hypothesis is true. There's 3 cases: the left tail, the right tail, and the 2 tails. The p-value is just for the left tail, which is this case, the p-value is just the area to the left of that statistic. So this is the test statistic. And then from here to the left should be the p-value. So the p-value is the area to the left of the test statistic. And then for the right tail, the p-value is just the right area from the test statistic. And then the one in the 2 tails, we just have to take twice the area in the tails beyond the test statistic. So I take this area, I multiply by 2 because this is 2 tails. They are symmetrical. They are symmetrical for the z statistic. That's why we can take just one portion, either from the left or from the right, and then we multiply that by 2. Now, for the p-value methods, if the p-value is less than the significant level alpha or the type 1 error, then we reject the null hypothesis. If it's bigger than alpha, we fail to reject the null hypothesis. Okay, the next one is the critical value methods, or sometimes we call this to be the traditional methods. Now, we can find the critical value methods by just finding the critical values that separate the critical regions, where we reject the null hypothesis from the values of the test statistic that do not lead to the rejection of the null hypothesis. Now, after we find the critical value, if the test statistic is in the region of the critical value, then we reject the null hypothesis. Or if it's not in the critical region, then we fail to reject the null hypothesis. Alright, so that is the end of the introduction to chapter 8, and the next section we'll learn how to make a claim for the population proportion. And thanks for watching.